All right, this is part 2 of Unit 6, and we're looking at the buffers. Specifically, we're going to start by talking about how if you have a common ion present and you are dealing with equilibrium, you can kind of see why it is that there's only a slight shift as opposed to a pretty dramatic change in the pH when you have a buffer present. So if you do have an ion that's common, it will cause the equilibrium to shift in one direction versus another. So in this particular one, adding a source of sodium chloride provides a source of chlorine ions. Ions are on the product side. So by adding chloride ions, you actually cause the equilibrium shift back towards silver chloride, therefore making more precipitate. If you neutralize acid or base and you make more of a conjugate base or conjugate acid, that's going to cause your pH to shift slightly, but not nearly as much as if there was nothing that could neutralize that addition, which you saw in your lab with water and with salt. Okay, so the pH of a weak acid, in this particular example, acetic acid, pH is around 2.7. And then when you have the conjugate base of that acid, sodium acetate, your pH is going to be a little bit higher. You mix these two together, and this has got an indicator in it to show kind of a visual as to what the pH level is looking like. When you mix them together, you see that the pH kind of falls in between them. And the pH will vary depending on which one of those two components you have more of. But because of that common ion, is not going to cause the pH to rise drastically if you add base to it. It's also not going to cause the pH to drop dramatically if you add acid due to the presence of that sodium acetate. Okay. When the pH of 75 mils of 0.15 molar HC2H3O2 has been had 0.002 moles of sodium acetate added to it, what would happen? So I'm going to show you a way to do it in this particular example that you won't have to use again. This one's going to involve just doing traditional equilibrium. And then I will show you an equation called Henderson-Hasselbalch that will allow you to use as a shortcut to kind of make this a little bit simpler. So when acetic acid is added to water, it's going to donate its hydrogen proton, leaving behind acetate ions and H3O+. If we have 0.15 molar HC2H3O2 present, sorry, we've got our Ka expression, and we know that to write the Ka expression in terms of these reactants and products, it would be H3O plus and C2H3O2 minus over HC2H3O2. The concentration of sodium acetate is going to be determined, determine the concentration of the acetate ions. Since this is an ionic compound, it is soluble. The alkaline metal will dissociate from the acetate ion, and we know the moles we have of the sodium acetate, and we know the volume we have, because when you add it to the 75 mils, we're going to go ahead and say the volume isn't really going to change. So by taking the moles of the sodium acetate and dividing it by the volume, we get its concentration, 0.0027 molar. Now, the acetate ions aren't going to react with the acetic acid. They're actually part of the acetic acid. And what that's telling us now is that we have the concentration at equilibrium, 0.15 molar, of the acetic acid, and we have the concentration of acetate ions, 0.0027 molar. We also know what our K value is, that it's 1.8 times 10 to the negative fifth. So if we know that, and we know the concentration of the acetate ions and the acetic acid, we should be able to find the hydrogen ion concentration. By solving for H3O+, we get that that concentration is 1 times 10 to the negative third molar. Our pH is the negative log of our hydrogen concentration, and so that would be 3. Okay? I promise there's a shortcut. And this next example, rather than me giving you the equilibrium concentrations, I'm telling you you have 0.43 molar ammonia, and we're going to add hydrochloric acid, a strong acid, to that base. Well, the first thing that the ammonia is going to want to do in the presence of hydrochloric acid is neutralize it. But when ammonia is placed in water, It makes ammonium ions because it accepts a proton from the water, and it makes hydroxide ions. And the Kb expression for that would be your products over reactants, NH4 plus OH minus over NH3. We can't go straight to our equilibrium expression this time because we have to use up the strong acid as much as possible, especially if it's limiting, and I believe it is in this case. You have a volume and you have a concentration for the hydrochloric acid, which is your source of hydrogen ions, and you have a volume and a concentration of your ammonia. So we need to find the moles we have of each of those so that we can figure out which one is limiting. And so I multiplied molarity times volume to give me moles of ammonia and moles of hydrogen. And initially I don't have any NH4 plus present. When I look at the two quantities I have present initially, I see that the hydrogen concentration, or the hydrogen amount, is smaller than the ammonia. So that tells me that the hydrogen amount is limiting, and that's what I'm going to use up completely. And so the ammonia will also go down by that amount, and the ammonium moles will increase by that amount. So that leaves me with 0.0080 moles of ammonia and 0.0030 moles of ammonium ions. Since I now know what I have present at equilibrium, I can account for their increase in volume by adding the two volumes together and get their new concentrations. Ammonia's concentration would be 0.008 moles divided by 0.05 liters, 25 plus 25 giving me 50 mils. If I do the same thing with ammonia, I would take, oops, sorry, snow stepped on the computer screen. If I take ammonia, 0.003 moles, and I divide it by 0.05 liters, I get its concentration as 0.06 molar. Since my Kb expression is equal to the NH4 plus and OH over NH3, and I know what two of those are, I know what the ammonium is, and I know what the ammonia is, I should be able to solve for hydroxide, and I get that it has a concentration of 4.8 times 10 to the negative fifth. I can use that to find pOH, and from pOH I can find pH. And so when you add the hydrochloric acid to the ammonia, it does cause the pH to drop, and the buffer forms having amounts of both ammonium and ammonia in your mixture. So when you have a buffer, when you have a weak acid and its conjugate base, or a weak base and its conjugate acid, it's able to resist changes or dramatic changes in pH when you add small amounts of strong acid or strong base, hydrogen or hydroxide. You do have to have both present. You have to have both the weak acid and the base, or the weak base and the acid. And you have to have an acid-base combination in terms of that conjugate pair that doesn't react with each other. If it does react in the form of a strong acid or strong base, then you will have to neutralize that strong acid or strong base as long as the buffer can handle it. So here are two particular examples. We have an acid buffer in the first example, and we have a basic buffer in the second. Hydrofluoric acid and sodium fluoride, with the fluoride being the conjugate base of HF. We see in the presence of strong base, we make water and fluoride ions, so the weak acid is able to neutralize the hydroxide, and the fluoride ions in the presence of the acid make hydrofluoric acid and water. Okay, so the conjugate base can neutralize the acid, and the weak acid can neutralize the strong base. Ammonia, the weak base, and ammonium, which is our conjugate acid, the chloride is going to be soluble. I think if you recall your solubility rules, we will see that all ammonium compounds are soluble. The weak base, the ammonia, can neutralize any acid added until it's used completely by accepting a proton to make that conjugate acid in water. And the ammonium ions can react with the strong base to make water and ammonia. Okay, so your buffer has to be able to neutralize both the acid component as well as the basic component. So I've shown you how to do this with equilibrium. What I'm going to show you now is how to do this with the Henderson-Hasselbalch equation. But you always have to remember that if you have a strong acid or strong base added to a buffer or a weak base or weak acid, you need to see if you can neutralize that strong acid or strong base whenever possible, just like we talked about. And then you can use your equilibrium expression to determine what the pH will be depending on what's remaining. Okay? And so these are your Henderson-Hasselbalch equations. You're typically just going to be using the first one. And what they've done is take that equilibrium expression and solve for hydrogen, use that to get pH. And when they did that and all the other various mathematical manipulations, they were able to determine that pH would equal the pKa plus the log of your base over your original acid. Again, we know that the top one is your base because it has one less proton compared to your acid. And if you were going to use the POH equation, you need to just basically reverse everything. Instead of pKa, you use pKb. And this time the base, the acid will be on top. It has one more proton. And then the base would be on the bottom of the log ratio. So we're going to calculate the pH of a buffered solution made by adding 1 mole of ammonium chloride to 1 liter of 0.75 molar ammonia. Okay, we don't have to do stoich this time because ammonium is the conjugate acid of ammonia, so those are not going to react together. They're both weak. We need to have something strong to neutralize the weak base before we would have to do the stoich part. So we can go ahead and go straight into our Henderson-Hasselbalch equation. We do need to find the Ka of ammonia or ammonium because ammonia is our base. We want the Ka of ammonium. All right, and the Ka of ammonium on your chart is 5.6 times 10 to the negative 10th. To get the pKa, I would take the negative log of that value, which would give me 9.25. So my pH is equal to 9.25 plus the log of my base, which is the ammonia, over my acid, the ammonium ions. 1 mole over 1 liter would give me a ratio of 1. Now what's really nice about Henderson-Hasselbalch is because these are a ratio together in the same mixture, you can use moles for the concentration of A- and HA as long as moles are used for both, or you can use molarity, but it doesn't make a difference which way you go. So by adding the ammonium, we would expect the pH would drop slightly from the pKb of ammonia. We have the pKa of our acid, so it actually is probably going to go up just a little bit. Okay, I lied. Because we had more acid than base, that's what caused it to drop slightly. And it went down to 9.13. Okay? So this time we're going to add sodium hydroxide, a source of strong base, to 1 liter of the solution we had in A. And remember the solution we had in A? This one here has both ammonia and ammonium chloride present, so we need to account for the fact that both are present in our mixture. The base is going to react with the conjugate acid, so the hydroxide is going to react with the ammonium. We have initially present 1 mole of ammonium ions, and we also have initially present 0.1 moles of hydroxide. And from the 0.75 molar solution of ammonia, which we had 1 liter of, we have 0.75 moles of that ammonia. So if we look at these two, the ammonium and the hydroxide, we see that the hydroxide is our limiting reactant, so we need to use that up. Again, because this is stoich, we want to use up the strong base whenever possible, so we're not going to be dealing with the equilibrium shifts. We know that we're going to go from the reactants to the products. So 0.1 moles is removed from both the ammonium and the hydroxide ions, and 0.1 moles of ammonia is made, leaving me with 0.9 moles of ammonium and 0.85 moles of ammonia. So now that I know what I had present after I used all of the base that I added, the strong base, I can use my Henderson-Hasselbalch equation. pH would equal 9.25 plus the log. My base again has 1 less proton, so the 0.85 moles would go on top, and the 0.9 moles for the ammonium ions would go on the bottom. If you had divided these both by 1, you would have gotten the same for their concentrations, but that would work regardless of whether the volume was 1 or something else. So this time that ratio is going to be closer to 1 because we added base, if we compare that to the pH in our first one, I think it was like 9.13, I expect our pH is probably going to go up just a little bit, and it went up to 9.23. So it moved up by 0.1 because we had to use up some of the acid to neutralize the strong base that was added. This time we're going to add hydrochloric acid, and the hydrochloric acid, the strong acid, is going to react with the basic part of our buffer, which in this case would be ammonia, since it has one fewer proton. Ammonia reacts with the hydrogen ions to make ammonium. All right, and we see here that, again, we're moving from reactants to products. Because we're dealing with 1 liter of the solution in part A, we're going to have basically the same amounts we had in part B. We still have 0.1 mole of our acid this time, but the ammonia, we started with 0.75 molar, 1 liter, so now we have 0.75 moles. The 0.1 moles of hydrochloric acid was provided to us in part C, and we have 1 mole of the ammonium ions. The hydrogen ions are our limiting reactant, so we reduce the reactant side by 0.1, and we increase the ammonium side by 0.1, leaving me with 0.65 moles of ammonia and 1.10 moles of ammonium ions. So our acidic part of our component has increased, so when we use our Henderson-Hasselbalch equation, we should see that the pH is actually going to drop from that 9.13 we saw in the first part, in part A, and we see that it did drop to 9.02. So buffering capacity basically represents the amount of hydrogen or hydroxide you can have in a buffer, or you can add to a buffer without a big change in your pH. The bigger that capacity is, the more you can add hydrogen in the form of protons or hydroxide ions without seeing a change. So the more concentrated your weak acid or weak base is, along with its conjugate partner, and the greater the volume is you have of that buffer, basically the more those values are larger, the bigger your buffer capacity is going to be. So if you had fairly large amounts of these following 3 buffers, H3PO4 and NaH2PO4, weak acid, conjugate base, 1 less proton, NaH2PO4 and Na2HPO4, 1 less proton, and then finally here Na2HPO4 and Na3PO4, 1 less proton from the HPO42- and the PO43-. Which one would be able to work best at a pH of 7? So if you had roughly equal amounts of both, basically the pH is going to be determined by your Ka value, and the pH would be relatively equal to your pKa value. So if I go and look on my chart, I can find the Ka's of phosphate, or phosphoric acid, dihydrogen phosphate, and hydrogen phosphate ions. So the Ka of phosphoric acid is 7.5 times 10 to the negative third. So the pKa would be roughly 2.12. This would probably be too acidic of a buffer to give you a pH of 7 without you drastically increasing the dihydrogen phosphate ions you have present. In part B, Ka of H2PO4- is 6.2 times 10 to the negative 8. So your pKa would be roughly 7.21. That one wouldn't be nearly as hard to get. You would probably need to add a little bit more of the acidic component of your buffer, but you would still have relatively large amounts of both components. And then finally in part C, HPO42- has a Ka of 3.6 times 10 to the negative 13. When you take the pKa of that value, it's 12.44. It would probably be, if not impossible, very close to get a buffer down to 7 without basically destroying your buffer by adding acid to it. Okay, so this should get you through the buffer part of your homework for part 2 of this unit.